So this is another problem involving motion along a straight line. There's a station 1 and a train starts at rest from station 1 and it travels to station 2. So the subsequent velocity versus time graph for that motion of the train is shown here. You can clearly see there are three stages for this motion. This is stage 1, this is stage 2, and this is stage 3. We want to first describe the velocity, the acceleration in each of these stages. So that's part A or part 1 of this question. Second part is calculate the total displacement of station 2 from station 1. So that's the second part. So let me first draw kind of a sketch of what's going on. So this is a horizontal straight track. That's what we are assuming. And let's say just like in the usual case, right hand side is the positive direction. So this is positive direction. That means if we have a vector along this direction, that's positive. If a vector is towards the left hand side, then that's going to be negative. And then you should realize what are the vectors, right? Velocity, acceleration, position, displacement, those are all vectors. Distance and speed, they are just magnitude, they are not vectors. Okay, so let's start. So I'm going to say the starting point for this motion, I'm going to define it as t equals 0. At that moment, the velocity of the train is 0. So I'm going to show the train by this rectangular shape. That's our train. It's at 0 at the beginning, and that corresponds to this point. You can see a point over here, 0, 0 point is that point in time. And after 10 seconds, the train is moving to the right. We don't know the displacement of the train, but they give us the time. Now at t equals 10 seconds, the train has achieved a velocity in that right hand direction that is 20 meters per second. So that's a positive number, right? Because it's to the right. So this is motion, stage 1 motion. And clearly you can see the velocity starts from 0 and after 10 seconds it increases to 20 meters per second. As a result, there's a speeding up process. So there has to be some sort of an acceleration during that stage. There's change in acceleration, and let me call that acceleration A, and we want to figure out, and obviously you can see it's speeding up. As a result, the direction of the acceleration is the same direction as the velocity. Otherwise, there cannot be any speeding up of the motion, right? So that's we figure that out. Now, at the 60-second mark, so somewhere here, the train is still traveling at that 20 meters per second velocity it gained at the 10-second mark. So in time, when 60 second hits, the train will have the same plus 20 meters per second velocity to the right hand side. So what does this mean? It means from 10 seconds to 60 seconds, the train is not changing its velocity. So that signifies this part. You can see as time goes on, the velocity is the same. In stage 1, you can see as time goes on, the velocity value, look at this vertical part, it's increasing. It's increasing up to 20 meters per second. So here for the second stage, since we don't see any change in acceleration, we can call that part A prime. The acceleration is 0. This is what we call constant velocity motion. For that, the acceleration has to be 0. So that's stage 2. Now, Now let's look at stage 3. At 60 seconds, it's plus 20 meters per second. But look what happens as time increases beyond the 60-second mark. The velocity is now decreasing in the positive direction. And at the 80-second mark, the object comes to a rest or it stops. So I'll call it V final is equal to 0. Over here, the train is moving like that. So this is t equals 80-second mark, the acceleration. We want to find the acceleration, and let me call that a double prime, because just to differentiate this velocity from the rest. Now, what do you think about the direction of the velocity? Direction of the acceleration. Direction of the velocity is to the right. It's slowing down. The object is slowing down and come to a rest at the 80-second mark. So that means the velocity should be in the opposite direction. Since it's in the opposite direction, we should get a negative value for that. And then you can even convince yourself, look at the slope. The slope, look, the slope makes a larger than 90-degree angle with the horizontal, with the positive x direction. So that's definitely a negative slope. Over here, with the positive x direction, the slope makes a less than 90-degree angle. So for the first stage, the slope is positive. For the second stage, the slope is 0. For the third stage, the slope is negative. Okay, so now let's try to get some numbers. For example, let's calculate stage 1 motion. Okay, so we can conclude that velocity increases from 0 to plus 20 meters per second. So that's what happens with the velocity. Acceleration is constant. Now, why do I say it's constant? Because look at the slope. Rise over run for a velocity versus time graph gives us the average acceleration. But here you can see the average acceleration is constant, and that is the same value as the instantaneous acceleration at all these points. So if the average acceleration equals the instantaneous acceleration, what do we call such acceleration? I did explain this earlier. It's called constant acceleration. So the acceleration is constant, and we can find a value for that, right? So A is equal to the change in velocity divided by the change in time. Now remember, this is what we use to find the average acceleration. But since from the looks of this slope, it's a straight line slope. So that means at any point, the instantaneous acceleration is the same, and that has the same value that of the average acceleration. So it's constant acceleration. So now we can find out instantaneous final velocity minus instantaneous initial velocity and the corresponding times t final minus t initial. You can see v final is plus 20, v initial is 0 because the motion starts at 0. Plus 20 meters per second happens at 10 seconds, and the starting point is like 0 time. So then you can see this is plus 2 meters per second square. So that's the answer. That's the acceleration for the first stage of motion. And the plus sign tells you that it's the same direction as the velocity. Now stage 2. Stage 2 motion. velocity remains the same. Velocity remains the same. You can see for a velocity versus time graph, if you have a horizontal line, that means constant velocity. Velocity remains the same at plus 20 meters per second. As a result, acceleration is 0 for this stage, because since for a non-zero acceleration, there has to be a change in velocity. There has to be a change in velocity. This is very important. Always we have to look for a change in velocity if we want to see an acceleration. Always remember, change in velocity and acceleration go hand in hand. Now if we analyze the stage 3 motion, that is this part of the motion, you can see the velocity changes from plus 20 meters per second to 0. So that means there's a slowing down process happening, and this is clearly seen if you look at the slope. The slope is again constant because it's a straight line, but this time the slope is a negative value because it makes a larger than 90-degree angle with the positive x-axis. So that means this side. So if you look at this angle, this is larger than 90 degrees. That means you have a negative slope. Okay. So then the acceleration, we can figure that out again. You have to realize that since this is a straight line slope, a constant slope, the average acceleration equals the instantaneous acceleration for that part of the motion, and we say that we have constant acceleration. Okay, so let's look at what that constant acceleration is. Let me call that a double prime, because it has to be different from the acceleration in the first part, the acceleration in the second part. So that's why I'm putting a double prime, and this is again a change in velocity divided by a change in time. The velocity is final instantaneous velocity minus the initial instantaneous velocity divided by the corresponding times for those instantaneous values. So that means t final minus t initial. So that means the v final for this part is 0, right? Because it comes to a complete stop at the 80-second mark. So it's 0 minus v initial for this third part is this value over here. That is the 20 meters per second in the right hand side direction. So plus 20 over the t final value is 80 minus the t initial value. This is an initial ti, so that would be 60. So here you are going to get a minus 20 over minus 20, making it minus 1 meters per second squared. So that is the answer for this third stage. The acceleration is minus 1 meters per second squared. So let me do this. So a double prime is minus 1 meters per second squared. So that what does that mean? It means that the direction of the acceleration is opposite to the direction of velocity. You can see plus meaning to the right, minus meaning to the left. So the object for this stage 3 is slowing down, and we call it deceleration. So the motion, so this is deceleration. This is deceleration
of the object. So that's what we see in this part. There's a deceleration. Okay, now so this is the end of part A of this problem. Now let's look at part B, where we need to find the displacement. So if we look at this figure, the displacement from station 1. So let's say now we are looking in terms of the position. Let's say this is station 1 and this is station 2. Now we need to find the displacement, the change in position between these two points. Now I told you in my lecture video that the displacement can be obtained by a velocity versus time graph simply by looking at the area between the line and the time axis. So that means this region provides us the displacement for this motion from station 1 to station 2. That's how we get the displacement. So let's look how to do that. Okay, so this is part B of this example. We need to find the position between station 1, the displacement between station 1 and station 2. So that means the change in position. As I told you, the change in position or the displacement is given by the area between the line. So that is this blue line over here, the line and the time axis for a velocity versus time graph. This only applies, remember, for a velocity versus time graph. So that means this shaded area. So I'm going to shade this region. That's the area we want to figure out. So now my question is, how are we going to figure out this area? So this goes back to high school geometry. It's area of a trapezoid. So you can see here a large trapezoid. Now if you cannot remember the area equation for a trapezoid, that's totally fine, because you can see within that trapezoid there are three elements, two right angle triangles and one large rectangle. So either you get the area using the large trapezoid, or you get the area by summing up all these three components, the two right angle triangles and the larger rectangle. So either way you should get the right answer. I'm going to use the easy method, that is use the area of a trapezoid to get the displacement. So the displacement is equal to area between the line and the time axis. Okay, now you can see this line is on the positive side. That means our displacement is positive, because displacement can be positive and negative, right? Because it's a vector quantity. For example, how about this one? So before doing this problem, I'll just give you an idea about another type. So let's say that we have a velocity versus time graph like this. So there's a negative axis for velocity. So let's say something like this. We have the same pattern, and now there's a part going towards the negative side of the velocity axis. So now what would be the total displacement for this entire time period? So let's say that you get an area over here, let's call it A, and let's call this area B. You should realize that A is on the positive side of the velocity. So that's a positive displacement. Since B is on the negative side of the velocity axis, B is a negative displacement. So then the total displacement or net displacement for this situation would be plus A plus minus B, or simply you can write it as A minus B. So keep that in mind. This is very important. Maybe you might get one or two multiple questions out of this sort of a thing, because this happens since the displacement is a vector quantity, as a plus value for displacement as well as a negative value for displacement depending on the direction, right? However, in our problem, it's straightforward. It's only along the positive velocity axis, so our displacement is going to be positive. And that should be clear to you if you look at this figure, because I told you everything is moving along the positive direction. So there's nothing moving towards the negative direction, so there cannot be any negative displacement in this problem. Uh, so, um, so let's take a look at this example again. So area of the line between the line and the time axis is the area of the trapezoid. So that is 1/2 times the length of these two parallel lines. So the longer parallel line, that is 80, plus the shorter parallel line to that one is 50, right? Because you have, that means this distance 60 minus 10 is 50, and then we have to multiply this by the height. The height is 20, and this is 130 multiplied by 10. And what are the units? The units should be meters, right? Because meters per seconds multiplied by seconds gives us the unit of displacement, and that is meters. So you can see, to be very correct, let's put the positive sign, and 1300 meters or 1.3 kilometers is your answer. So that's the displacement from station 1 to station 2.